You've seen it, right? A gecko just casually walking up a glass window or hanging out on the ceiling like it's no big deal. It's like it's defying the laws of physics. For literally centuries, this has been one of nature's biggest and best-kept secrets. But now, well, thanks to some really incredible science, we're finally starting to crack the code.
So what is the source of this superpower? I mean, really, what's going on here? It's not suction cups, and it's not some kind of sticky goo. The real answer is so much more elegant and way more complex. To really get it, we have to take a journey from the world we see every day all the way down to the level of individual molecules.
All right, let's dive in. Our whole investigation starts by zooming in on a gecko's foot. And I mean really zooming in. We're about to explore a microscopic world, a tiny forest of structures that hold the key to its mind-bending grip. So this is the first level of this incredible natural tech. A gecko's toes are covered in these ridges, and those ridges are packed with millions of tiny, flexible hairs called setae. Each one is way thinner than a human hair, and believe it or not, we're just getting started. And it just gets crazier from there. Every single one of those millions of setae branches out again, splitting into hundreds of even smaller filaments. The sheer number of these things is just mind-boggling. It creates this massive surface area, and we're still not at the true source of the stickiness.
And here it is. This is the final layer, the big secret. The very tips of those branches flatten out into these tiny triangular pads called spatula. Now we're talking on the nanoscale, so unbelievably small you could fit billions of them on the head of a pin. This is where the real magic happens.
Okay, so the stickiness all comes down to a fundamental force in physics called van der Waals forces. The easiest way to think about it is like a super weak static cling that happens between molecules. The cling from just one spatula is basically nothing. But, and this is the key, when you have billions upon billions of these spatulae all making contact with the surface at once, those tiny little forces add up to create an incredibly strong bond that's also somehow easy to release.
So we know what makes it stick, these spatula and these forces. But scientists wanted to know how. How do all these parts work together as a dynamic system? The problem is, you can't actually see this happen in real time. And trying to simulate it is a huge challenge because you've got to model the big, flexible hair bending and the tiny molecular stuff happening at the tip, all at the exact same time.
So, for a long time, scientists had two different tools for this kind of problem. On one hand, you've got molecular dynamics, or MD. It's perfect for seeing the tiny world of atoms, like how a spatula actually sticks. But it can't handle something as big as the whole hair. For that, you need the finite element method, or FEM, which is great for modeling how bigger structures bend and flex. The problem was, neither one could give them the whole picture by itself. So what did they do? They did something brilliant. They built something totally new. It's called a concurrent multiscale model. This hybrid approach basically runs both simulations at once, combining the atomic-level detail of MD for the little spatula with the big-picture structural mechanics of FEM for the rest of the hair. It's kind of like having two different types of microscopes pointed at the exact same spot at the exact same time. Now, the secret sauce that makes this whole thing work is something called a bridging domain. You can think of it like a digital handshake or a translator sitting between the two simulations. In this zone, the forces from the tiny molecular world get passed up to the big structural model, and the bending that happens in the big model gets passed back down. They're in constant communication, talking to each other in real time. So they built this incredible virtual experiment. What did it actually let them see for the very first time? What secrets did this digital gecko foot reveal about how it sticks, and maybe more importantly, how it unsticks with such perfect control? The experiment itself was actually pretty simple and elegant, designed to mimic what you'd do in a real lab. So step 1, they preloaded the virtual hair, basically pushing it down onto the surface to make sure all those spatulae got a good grip. Step 2, they let it relax for just a moment. And finally, step 3, the pull-off, where they pulled the hair away and measured the force second by second until it completely let go. In this graph, right here, it tells the entire story. You can see the force go up, that's a positive force, as they push down. Then, as they start to pull away, the force dips into the negative. That's the good stuff. That's the adhesion, the stickiness. And you can see it hits this peak of over 280 nanonewtons before the spatula finally start to pop off. The simulation also showed something fascinating. How the spatula lands makes a huge difference.
What they call a pad-dominant contact, where the flat part lands flush against the surface, creates a way stronger bond than a tip-dominant one. This basically proves that the gecko has this amazing, fine-tuned control over the angle of its feet to get the best possible grip.
So what did we learn from all this? Well, first off, that gecko adhesion is way more than just sticking. It's a dynamic dance of peeling, sliding, and bending. And get this, a little bit of sliding sideways can actually make the grip stronger and last longer. And maybe most important, the spatula don't all just let go at once. It's a sequential process. They peel away one by one, which gives the gecko incredible control over unsticking.
Now, this isn't just about understanding a cool lizard. I mean, it is cool. But decoding this secret actually gives us a blueprint from nature on how to build the perfect adhesive. So let's talk about how this could totally change the technology of our future.
There's a name for this whole field. It's called biomimicry. It's a really simple but powerful idea. We're looking to nature, which has had millions of years of R&D, to find elegant solutions for our own engineering problems. And it turns out the gecko is an absolute master of nanotechnology.
And the potential here is, wow, it's just incredible. I mean, just think about it. Imagine tapes you could use thousands of times that never lose their stick and never leave any gunk behind. Or robotic grippers in factories, or even in space, that can pick up super delicate objects with precision. We could even see medical devices that can stick safely right onto human tissue. The possibilities are really, truly amazing.
The gecko's foot really is a marvel of natural engineering. It's a perfect adhesive system that we are only just beginning to truly understand. It really makes you wonder, doesn't it? As our scientific tools get more and more powerful, what other secrets, what other natural superpowers are hiding out there in plain sight, just waiting for us to look close enough to see them?